money, time in doing something or in producing a desired result. Let's say you have 1 hour to study and you do really a study in um, 55 minutes. You study 55 minutes of that and you just compare it for 55 minutes study. You have 60 minutes to study, but you're using 55 minutes of that 60 minutes to a study. Compare it to the case that you have 60 minutes of the time, but you do 30 minutes a study. Which situation is more efficient in terms of studying? Of course, that one, right? Because you're spending more time compared to this one. So efficiency is um, ability to avoid wasting materials, energy, or time. No, here. When energy transfer from one form to another based on a law of conservation of energy, none of the energy is destroyed or lost. Okay, let's just try to understand that. Um, According to conservation of the energy, what the energy not being destroyed, right? Is just transferring from one form into another form. However, some is transferred into form of non-intended for this purpose. Like what? When you are, let's say, running on a street, makes noise, some of the energy will be wasted in terms of the heat. Now, incandescent light bulb transfer electric energy to 5% light and 95% heat. So looking at the second example, I think is more makes more sense. When you have a light bulb, you use electricity, right, to turn it on. But is that total electricity that you input into the light bulb? Would all of that turn into light? No, 95% of that will be wasted as heat. When you touch the light bulb, it's so hot, right? Seems that loss of that energy transfers to the heat. We don't use the heat. We don't need heat. We need the light, right? And 5% of that going to the light means if you are putting 100 have 100 joule of electricity, the energy electricity, 5 joule of that will be used. So the efficiency will be 5 over 100 multiplied by 100 would be 5%. Is the efficiency of this light bulb is 5%, which is very low efficiency. Now, efficiency is output divided by input. Output is something the useful work that you do. Input is the energy that you put into the system. We'll do lots of example, I guess, and it makes better sense why we're doing. Okay, let's just look at this question. A child weighing 55 kilogram run on the top of a hill with his toboggan. If the hill is 22-meter tall and his final speed at the bottom of hill is given, how efficient was this process? Okay, so the person is here at the top, right? And is slide down, going to the bottom. The mass is given 55 kilogram. Um, the hill is 22-meter high. Um, V0 is 0 here, and we have a V final is 5.4 meter per second. Okay, now the useful work is when it's sliding down, this object, the gravity do the work, right? Is really down. Maybe I just make it better, guys. This is the force, right? F of g is downward. The gravitational force doing the work. I have other force F of normal, but since this is perpendicular into um, direction of the movement, I will not take care of that. Uh, the gravity do the work, gravitational force do the work, right? So if I tell you, maybe even I don't need to mention that. If I ask you how much work is done when the object slide from this top to this top to this bottom, what would you say? How much work is done? How much work we did put into the system? Maybe energy of input. Energy input is going to be total energy the child possessed, right? At the beginning. Child total energy at the beginning on top of the field. On top of field, right? And what is that? E total over there is kinetic plus E potential, right? I call it point 1, which is half mv2 plus mgh. I know velocity was 0, so just it possessed potential energy. The mass, maybe I just keep it like that. I call it h1, right? Let's just keep it like that. Total energy at the beginning, that would be your input. Now, what would be the output, right? What is the output? So the output would be total energy at the end, at the bottom of hill, right? Again, gonna be E kinetic at point 2 plus E potential at point 2. I have half mv power 2 mgh. Since the h here is 0, right? We do not have that. I call it V2 here. Now I know efficiency is output divided by input, right? Multiplied by 100. The output is half mv over 2. Input is mgh1. M and n cancel. And I'm just going to put the number. The velocity here is 5.4 power 2. G is 10 and h is 22. 5.4 power 2 divided by 2 divided by 10 divided by 22. And I forgot to put 100 here. Okay, multiplied by 100. It's going to be 6.6. So what happened to the rest of the energy? What is happening from the top of field to downhill? Can anyone tell me why the output energy is much more smaller than input? What happened in here? Can anyone turn on the mic and tell me? Anyone? There's some energy lost somehow. How we did happen that we lose the energy? We're saying that energy won't be destroyed. Do you think the energy was destroyed? Any thoughts? No one? Okay, the energy wasn't destroyed. It's just turned into the heat, right? The friction between the child and that toboggan and the earth there was some contact surface between them, right? So uh, there was friction, and friction caused some of those energy turned into heat. That's why it's kind of moved, it transferred to another type of energy. Okay, does that make sense? Any question? Okay, second example.
Miss,
Yes.
how do you know the energy, the output energy is at the bottom of the hill?
So when you do some work, your final state give you the output. Let's say you want to lift something, right? Your input energy will be the muscular energy that you have, and output is how much um, how much work you have done on the box, right? It's just lifting that. That would be your output. Yeah, that's gonna be kind of in this situation. So different situation would be different, actually. Now, maybe we do more question and it makes more better sense. Let's just look at that. You throw a rock directly upward at a speed of 12 meter per second. If the rock went 5.2 meter in the air, how efficient was this process? Where did energy go? Okay, let's just do that. So like this scenario, let's just discuss that. How do I know what is the input energy? The initial energy that the object possesses is your input because you are putting the speed into the ball. Like your muscles pushing the ball upward means you're giving the energy, and that energy would be the input energy, right? So energy input is total energy of ball at the beginning. Mhm. And what is the output? The output is how much work you have done, right? Work done by moving the object up. Now, input energy, this is easy, right? If I take the E potential zero to be when the ball is thrown up and when it's going to the highest point here, it is 5.2 meter tall. I want to see how much work is done from here to here. Okay. Input energy is EK plus EP, right? At point one, I just put that this one point one and this is point two. Kinetic energy, of course, we have some kinetic energy, right? Half m v1 power 2 plus potential energy at point one is 0. Now E output, it could be the work that is done from here to here, right? Um, we can look at this as two different ways. The work done is force multiplied by displacement, cosine of the angle between them, because I just want to find the energy output. I know just the mg doing the work, right? Force gravity doing the work, and it causes a stop. And the displacement is this d here, 5.2. Okay, this is one way of looking at that. Another way
I'm
is
sorry, Miss.
yes. Is this?
Can you a little like more explain why EP equals zero?
Sure. See, I put my level 0 to be at a place when you throw the ball up. Always you can choose your zero potential or zero height. You could choose that to be any point. I choose it to be at the beginning of this motion when you throw it up. So since the EP is mgh, and at point one, this is going to be at point one. H at point one is 0. So that would be 0, right?
Oh yes, thank you.
You're welcome. Okay, I could say that the output energy is the work done from here to here, right? The useful work. And work is change in kinetic energy. Or I could say that work is force multiplied by the displacement. Or I could use that work is equal to change in potential. And all of that give you the same result. I know the changing kinetic energy is the same as changing potential, and it's just gonna be mgh, right? And I know force multiplied by displacement is gonna be mgh at the end. Because this d here would be your h, right? Um, so it's kind of, you can think about it in different ways, but you will come up with this equation all time. So knowing the efficiency is output divided by input multiplied by 100. So is half, oh wow, okay, output is mgd divided by half mv power 2. Math and math cancel. Um, that would be multiplied by 100. I forgot that. I'll just put some number. 10 multiplied by 5.2 divided by half. Velocity, what was the velocity? It was 12. 12 power 2. Always, if you do this and you get the efficiency more than 100, you have done something wrong. You have to check it back. 10 multiplied by, because efficiency is always um, less than 100%, right? It's going to be 72%. 72.2%. Okay, any question? Okay, efficiency in real words. Maybe I just go to the type of energy. Okay, so we have two type of energy: renewable energy and non-renewable energy. The substance with an unlimited supply of energy is renewable. For a supply of energy that can be replenished as it's used in energy transforming process. Non-renewable energy is substance that cannot be replenished as it's used in energy transforming process. It's like when you're using the water to produce electricity, is kind of renewable because you can replace it, right? So get the fossil fuel. So when you're using the fossil fuel and you burn it, as you cannot get the fuels back, right? So it burned and it turned to the carbon dioxide and so on and other products, but is not reversible. So not renewable and one of the most common form of energy consumed, right? So this is kind of um, why this is not a good way to produce energy, because it's taking hundreds of years for the animal and plants to decay to create a fossil fuels. And what we do when we run out of those resources, so we need to find another sources of energy, something that um, don't cause pollution, or when I think about someday they will not be available for us, right? Because we will run out of that. Okay, so another one is a nuclear energy. So it's not a clean energy, right? A form of potential energy produced by the interaction of the nucleus of atom. So you breaking the nucleus of an atom and because of that process, a huge energy will be produced, right? The nuclear fusions. Nuclear fusions are two type of uh, nuclear reactions. So nuclear fusion is formation of larger nuclei with two smaller nuclei. So you smashing two small nuclei and will produce a larger one, and that process huge energy will be released. And nuclear fission is breaking down a larger into a smaller. Uh, so I hope you remember Hawk. That was created, I guess, because of the nuclear reaction. Okay. And there are so many issues around the nuclear ion because nuclear is pollutes the water, it pollutes the waste from those nuclear power plants. It's really harmful for environment, and you already know it. Yes. Solar energy is another type of energy which is very clean and conversion of solar radiation into usable energy from in usable energy form done with the help of the photovoltaic cells. So these are the cells here. And when the light hit them, it produced some kind of electricity, current inside the panel. And the panel will store the energy in some battery, and you can use transfer the energy from the battery to the other places. Okay, so the issue around that is doesn't create enough energy. So we have to really this will work very hard and give us a lot of energy. Let's say in one day. And setup is expensive for average income, right? Hydroelectricity is another good one. Takes the kinetic energy of water and convert it into the usable form for us. The running water turns the turbine here. So let's say you have a reservoirs, you have a dam here. Um, why we have a dam? Because you want to store when it's raining, you want to store the water coming behind the dam, right? And then later on you use it to turn some turbine, and this mechanical energy will in turn into electric current, and then we can use it, right? What if you don't live by a body of water? So means not all area have a privilege to have a lots of water. For example, maybe in part of the Africa, they don't have that kind of weather. So, and that's the issue, right? Other renewable energy resources. So I'm encouraging you guys to read this one and let me know if you have any question. This is gonna be a self-study, that part, that table. I'm not gonna read that. And that's the